Before the interview, I have a quick announcement to make. In order to make this podcast better, I've released a survey to get feedback from you listeners. If you have a few minutes to spare, I'd greatly appreciate it if you could fill it out. It's linked in the podcast description, as well as on axerp.net. Now, on to the main show. Hello, everybody. Today, I'm going to be talking to Vanessa Kosoy. She is a research associate at the Machine Intelligence Research Institute. She's worked for over 15 years in software engineering. About 5 years ago, she started AI alignment research and is now doing that full time. She's authored 3 papers, but today we're going to be talking about her sequence of posts on Infra-Bayesianism that was co-authored by Alex Appel. So, Vanessa, welcome to Axerp.
Thank you, Daniel.
All right, so I guess the first question is, in a nutshell, what is Infra-Bayesianism?
Infra-Bayesianism is a mathematical framework that is meant to deal with the problem of non-realizability in reinforcement learning, or like in the theory of reinforcement learning. So the problem of non-realizability is that you have a certain hypothesis space that your algorithm is trying to learn. Like, it is trying to learn which hypothesis is correct. But the real world is not described by, the real world is described by none of those hypotheses, because it's much more complex than any model could possibly capture. And most of theoretical research, or virtually all theoretical research in reinforcement learning, focused on the realizable case, such as assuming that the world can be exactly described by one of the hypotheses. And like that's where Infra-Bayesianism comes in and kind of explains what happens when we drop this assumption.
Okay, so I guess how big a problem? I gather that this work is motivated by like AI alignment or ensuring that when we create like really smart AIs in the future, they're going to do what we want. How big a problem do you think non-realizability is for this?
Well, there are several reasons why I'm interested in this in the context of AI alignment.
Okay.
One reason is that one reason is just deconfusion, right? Like trying to understand what does it mean for a reinforcement learning system to operate in a non-realizable setting, and like how to think about this mathematically. The other reason is because if ultimately we want to have algorithms that satisfy formal guarantees, if we want alignment to be like provable in some mathematical model, then non-realizability is one of the issues we're going to have to deal with in that context. And a third reason, or it's like a third group of reasons maybe, is that there are multiple questions related to deconfusing AI that kind of hit this non-realizability obstacle. For example, the question of embedded agency, which Miri has been thinking about for some time and like promoting as one of the important problems, is something that's closely related to non-realizability. Because if your agent
what is embedded agency? I should ask.
Right. So embedded agency talks about agents that are part of the physical world, right? So like the classical approach to reinforcement learning is kind of viewing an agent as just 2 channels, input and output, and there's no physical world anywhere in the picture. And embedded agency is trying to understand how to fix that, because for example, human values are not necessarily expressible in terms of human inputs and outputs, right? So how do you think of that? And because of various failure modes that can happen because we are not taking into account in our models that the AI is actually part of the environment and not just like a completely separate thing. And this is closely related to non-realizability. And indeed, I have a program how to use Infra-Bayesianism, how to apply to understand embedded agency. And that's like one thing. Another thing is reflection. For example, agents that do self-improvement. That also very quickly leads you to problems of non-realizability. Because in reflection, an agent should be thinking about itself, right? But it cannot have like a perfect model of itself.
Why can't it have a perfect model of itself?
Well, it's sort of this kind of paradox because then it enters a sort of infinite loop, right? It's like why you cannot predict what it's like nobody can tell you a prediction of something of what you would do because maybe you will listen to this prediction and do the opposite or something like that. Or just you can think about it just complexity theoretically. Like the space of hypotheses the agent is working with, their computational complexity is lower than the computational complexity of the agent itself, because it needs to somehow work with all of those hypotheses. So the agent just is too big to fit into its own hypothesis space. Uh, it's really kind of similar to like self-referential paradoxes we have in mathematics, like in logic or other places. Yeah, but you can also view it as a special case of non-realizability. So information can help you there also. And another thing is decision theory. And this is something that we actually wrote about in the sequence, that Infra-Bayesianism basically solves all the paradoxes like Newcomb's problem and the other types of problems that Miri were writing about, like counterfactual mugging and so on. You know, the sort of problems that so-called updateless decision theory, or sometimes called functional decision theory, was invented for, but never fully mathematically formalized. Infra-Bayesianism solves those problems, or at least a very large class of those problems, in a way that's completely mathematically formal. Yeah, so we see that there's like a whole range of different applications.
Yeah, just getting on that last part for a second. For those who might not be familiar, what is decision theory? Like, what type of thing is decision theory trying to be a theory of?
Yeah, so decision theory is the field that talks about how do we think of making rational decisions mathematically. And I guess it began with the work of, or at least the mathematical side began with the work of von Neumann and Morgenstern, where they proved that expected utility maximization is like always the correct way to make decisions under some reasonable assumptions. And it developed from there. So like game theory and economics are all kind of offsprings of decision theory in some sense. And specifically, Miri and Yudkowsky wrote about some interesting paradoxes, like the Newcomb paradoxes that are a problem for classical decision theory, and it showed that our like understanding of decision theory is lacking in those specific examples.
So what is the Newcomb paradox?
Yeah. So the Newcomb paradox is the following setting. Uh, you're playing a game with some entity called Omega, and Omega is something very powerful. Omega is very smart, or it just has a huge computer, and it's so powerful that it can simulate you and it can predict everything you do, right? And that's completely like in theory, that's completely possible because we know that our brains operate on the laws of physics. So if you have a big enough computer, you could in theory predict everything that a person would do. And then Omega offers you a choice. You have two boxes and you need to choose, and there's money inside of them. And you need to choose either the first box or both the first box and the second box together. And this seems like a really silly question. Like, obviously, if you can choose only A or A plus B, then A plus B is always better than A. But there is a catch. And the catch is that Omega predicted what you would choose. And if you chose to take only the first box, then it put $1 million in that box beforehand, before the experiment, the game even started. If you chose to take both boxes, then the first box is going to be empty and the second is going to have $1,000. So the result is, what happens when we see someone picking the first box, like only the first box, they walk away with $1 million. And when we see someone picking two boxes, they walk away only with $1,000. So it seems like, in some sense, it is better to pick only one box. However, classical approaches to decision theory, like causal decision theory, which is like popular in philosophy, they would advise us to take both boxes. So something is wrong here. And philosophers have kind of debated these questions, but nobody until now gave a completely formal decision theory that kind of explains, why formally why you need to choose one box in this situation.
Okay. I should say, I think Evidential, there's this thing called Evidential decision theory that does choose one box in this scenario. Is that right?
Right. You have Evidential decision theory, which does choose one box, but then it fails in other situations. So it's like, yeah, and like, here the idea is that you want to succeed in all of the, like, all possible setups in which there is something predicting you and interacting with you. You want to be successful in all of this. So for evidential theory, for example, there is the XOR blackmail problem, in which evidential decision theory fails and causal decision theory succeeds. And then there is the counterfactual mugging problem, in which both evidential decision theory and causal decision theory both fail. On the other hand, Updata's decision theory is supposed to succeed in all of them, only that Updata's decision theory was not formally mathematically defined until Infra-Bayesianism.
Okay, so just to give listeners, I'm still going to ask preliminary questions, just to give listeners a better sense of, more of a sense, I guess, of what problems we're going to be trying to solve. What is this counterfactual mugging thing, which classical decision theories don't do well in, but your new updateless decision theory inside of Infra-Bayesianism is going to do well in?
Right, so counterfactual mugging is another game with Omega, and like before, Omega can always predict everything you will do. And this time, what happens is that Omega flips a fair coin. And if the coin falls on heads, then Omega comes to you and asks you for $100. And you can either agree to give them the $100, or you can refuse. On the other hand, if the coin falls on tails, then Omega might give you $1 million. But they only give you the $1 million if, in the counterfactual scenario, in the scenario where the coin falls heads, you would agree to give them the $100. So in this case, if you're the type of agent that would agree to give Omega $100, your expected profit in this whole scenario is like $500,000 minus $50. And if you're the type of agent who would refuse, then your expected profit is zero, which is much worse. But all like this classical decision theory would refuse to pay the $100.
Yeah, and this is basically, as I understand it, because like at the time they're asked the $100, basically like classical decision theories just say, well, I can either pay you $100 and get nothing, or I can not pay you $100 and not lose anything. And so from now on, my life is good if I don't pay you. And they're just like not considering about what would have happened in this like alternate universe.
Yeah, exactly. Like what happens is that in those scenarios, classical decision theory, they would choose to pre-commit to paying the $100 if they could, but if they cannot pre-commit, they have no intrinsic mechanism of doing so. They need like some kind of an external crutch that would allow them to make it for those scenarios.
Okay, so to summarize all of that, it seems like the point of Infra-Bayesianism, my read is that it's going to do two things for us. Firstly, it's going to let us have something like a good, I don't know, a good epistemology or a good decision theory about worlds that we could be in where like the real world isn't one of the worlds that we are like explicitly considering, um but like we can still do okay in it. And secondly, it's going to let us choose actions. It's going to give us like a decision theory that is going to solve these problems. Like we're gonna we're gonna be expected to do well in these problems where some other agent is simulating us and figuring out like what we are going to do or what we would have done had things turns out differently. Is that a fair summary of like what we want to get out of Infrabasianism?
It's sort of a fair summary. I would say that the second is really a special case of the first, because when we have agents that are predicting us, then it means that we cannot predict them, right? Because otherwise we have this again, this self-referential paradox. So agents that are, if our environment contains agents that are predicting us, then it means that necessarily our environment is not described by one of the hypotheses we're explicitly considering. So, like the ability to deal with worlds that are more complex and your ability to fully describe is what gives you the power to sort of deal with those Newcombian scenarios.
Okay, so one thing that people will notice when they start reading these posts is there's a lot of like math defined in the post, right? It's not just we're gonna have like bog standard probability distributions and go from there. Why do you need this new math? Why can't we just do all of this with normal probability theory that many listeners know and love?
Well, the thing is that like normal probability theory is kind of the problem here. The whole problem with non-realizability is that Bayesian probability theory, Bayesian epistemology, doesn't really work with non-realizability. Like when your environment is precisely described by one of the hypotheses in your prior, then we have theorems like the merging of opinions theorem, which shows that your predictions about what will happen will converge to what actually happens. But if your environment does not, like if your prior is misspecified, that's what something that's sometimes called misspecified prior problem in statistics, then there are no guarantees about what your Bayesian reasoning will give you. There are sometimes guarantees you can prove if you assume the environment is ergodic, but that's also a very strong assumption that does not hold in realistic cases. So Bayesian probability theory just
Oh, what? Yeah, when you say if the world is ergodic, what does it mean for a world to be ergodic? How could I know if my world was or was not?
yeah. So ergodic is like I won't try to give the formal definition, but roughly speaking, it just means that uh, everything converges to a stationary probability distribution. That's what ergodic means. So, like, if you're thinking of something like a Markov chain with a finite number of states, then it always converges to a stationary probability distribution after sufficient time. And like in physics, also like when systems reach thermodynamic equilibrium, they converge into a stationary distribution. And it's true that eventually everything reaches thermodynamic equilibrium, but in the real world, all the interesting things happen when we're not at thermodynamic equilibrium, right? And like when we reach thermodynamic equilibrium, that will be like the heat death of the universe. So that's like not a very interesting regime.
So, okay, now that so if we can't use normal probabilities, can you give us a sense of roughly what are the things we're going to be working with if we're going to try to be Infra-Bayesians?
Yeah. So.
And maybe this is going to explain why we're using the prefix infra.
Mm-hmm. Yeah. So Infra-Bayesianism. Well, Infra-Bayesianism, first of all, it's built upon something called imprecise probability. So I haven't really invented it from scratch. I took something called imprecise probability. Although when I had the idea, I did not really read much about the imprecise probability. I probably just heard the general idea vaguely somewhere when I started thinking about this. But anyway, so we took some concept called imprecise probability, which is something which is already known in decision theory in some contexts and is used for mathematical economics, for example. And we applied this to the theory of reinforcement learning. And we also generalized it in certain ways. So our main novelty is like creating this connection. And imprecise probability, what it does is it says, well, instead of just having one probability distribution, let's have a convex set. So formally a closed convex set of probability distributions. So for example, just to think of a very simple example, suppose we have our probability space has just two elements, right? So a probability distribution is just a single probability between 0 and 1. So what imprecise probability tells us is instead of using a probability, use an interval of probabilities. Like you have some interval between, I don't know, maybe your interval is between 0.3 and 0.45 or something. And when you go to larger probability spaces, it becomes something more interesting because you have not just intervals, but you have some kind of convex bodies inside the space of probability distributions. And then we did a further generalization on top of that, which kind of replaces it with concave functionals in the space of function. But if you want to just understand the basic intuition, then you can be just thinking of this kind of convex sets of probability distributions.
Okay. And I guess this gets to a question that I have, which is the fact that we're dealing with these convex sets of distributions, because that's the main idea, and I'm wondering how that lets you deal with non-realizability. Because just because it seems to me that if you have a convex set of probability distributions, in standard Bayesianism, you could just, have a mixture distribution over all of that convex set, and you'll do well on things that are inside your convex set, but you'll do poorly on things that are outside your convex set. Yeah, could you give me a sense of how maybe this isn't the thing that helps you deal with non-realizability, but if it is, how does it?
So the thing is, a convex set, you can think of it as some property that you think the world might have, right? Like suppose, just let's think of a trivial example. Suppose your world is a sequence of bits, so just an infinite sequence of bits. And one hypothesis you might have about the world is maybe all the even bits are equal to 0. So this hypothesis doesn't tell us anything about odd bits. It's only a hypothesis about even bits. And it's very easy to describe it as such a convex set. We just consider all probability distributions that predict that the odd bits will be 0 with probability 1. And without saying anything at all, like the even bits, they can be anything. The behavior there can be anything. Okay, so what happens is if instead of considering this convex set, you consider some distribution on this convex set, then you always get something which makes concrete predictions about the even bits. Like it's important to think, you can think about it in terms of computational complexity. or the probability distributions that you can actually work with have bounded computational complexity, because you have bounded computational complexity. Therefore, as long as you're assuming a probability distribution, a specific probability distribution, or it can be a prior over distributions, but that's like just the same thing. You can also average them, get one distribution. It's like you're assuming that the world has certain low computational complexity. So one way to think of it is that Bayesian agents have a dogmatic belief that the world has low computational complexity. They like believe this fact with probability 1, because all the hypotheses have low computational complexity. So like you're assigning probability 1 to this fact. And and this is a wrong fact. And like when you're assigning probability 1 to something wrong, then it's not surprising you run into trouble, right? Like even Bayesianists know this, but they can't help it, because it's just nothing you can do in Bayesianism to avoid it. So with Infra-Bayesianism, you can have some properties of the world, like some aspects of the world can have low computational complexity, and other aspects of the world can have high complexity, or they can even be uncomputable. Like with this example with the bits, your hypothesis, it says that the odd bits are 0. The even bits, they can be uncomputable. They can be like the halting oracle or whatever. You're not trying to have a prior over them, because you know that you will fail. Or at least you know that you might fail. That's why you have like different hypotheses in your prior.
So is the idea that thinking about the infinite bit string example, right? Is the idea that like in my head I'm going to think about, okay, there's one convex set of like all the distributions where all of the even bits are 0, maybe like there's another hypothesis in my head that says like all of the even bits are 1. Maybe there's a third that says that all of the even bits, maybe they alternate, or maybe they like spell out the binary digits of pi, or they're all 0 until the trillionth one, and then they're 1. Is the idea that like what I'm going to do is I'm going to have like a variety of these convex sets in my head, and the hope is I'm going to hit the right convex set?
So basically, it works just like Bayesianism, in the sense that you have a prior over hypothesis. So just in Bayesianism, every hypothesis is a probability distribution, whereas in Infra-Bayesianism, every hypothesis is a convex set of probability distributions, and then like you have a prior over those. And if the real world happens to be inside some of those sets, then you will learn this fact and exploit it.
Yeah, so think about the connection to the mathematical theory. So in the mathematical theory, you have these things called SA measures, and you have like these sets of these closed convex cones, which people can look up, but these sets of SA measures, and they're like minimal ones in the space. Is the idea that the minimal things in these cones, these are the like convex sets? And yeah, I guess I'm still trying to get a sense of like just exactly what the connection is between this description and the theory.
Yeah, so the thing is that what I described is what we call, in one of the latest posts, we called it crisp infra distributions. So a convex set of probability distribution, that's in some sense the simplest type, or like one of the simplest types of infra distributions you can consider. But there are also more general objects we can consider. And the reason we introduce those more general objects is to have a dynamically consistent update rule. Because like in ordinary Bayesianism, you have some beliefs, and then like some event happens, and you update your belief, and you have a new belief. And like you have the bias theorem, which tells you how you should do that. And we were thinking about, okay, how should we do that for Infra-Bayesianism? And we started with just those convex sets of probability distributions, which are just like something taken from imprecise probability. And with those objects, you do not have a dynamically consistent update rule. So you can still work in the sense of like just decide all of your policy in advance and follow it, but there's no way to do updates. Well, like the naive way to do updates is by sort of updating every distribution in your set. But that turns out to be not dynamically consistent. So like the behavior it prescribes after updating is not the same behavior it prescribed before updating. Because like the decision rule you're using with those config sets is the maximum decision rule. So you're trying to kind of you're trying to maximize your worst case expected utility, where like the worst is taken over this config set. And then when there are several things that can happen, then your optimal policy might be something that kind of tries to hedge your bets, something that tries to, okay, I'm going to choose a policy such that in neither of those branches I will do too poorly. But then when you're just in one of those branches and you're updating, you're kind of throwing all those other branches to the garbage and forgetting about them. Your like new optimal policy is going to be something different. So that's like the counterfactual mugging that we discussed before is like exactly the perfect example of that, where like just naively updating causes you to kind of disagree with your a priori optimal policy. So in order to have a dynamically consistent object rule, you need some object which is some mathematical object which is more general than just those convex sets of probability distributions.
Okay. And so the object you have are these convex sets of like souped up probability distributions, is my rough understanding?
Yeah, so there are like two ways to think about it, which are related by Legendre-Fenchel duality. Yeah, the way we introduce them initially in the sequence is we consider, so instead of just thinking of probability distributions, we think of measures that like measures that might not sum to one, and you also have like this constant term. Like you're thinking of a probability distribution that someone multiplied by a constant and also kind of added a constant, which is like not part of the distribution, but it's like added to your expected utility. And then you have a convex set of those things. And like with those things, you can have dynamic consistency, because this constant term is kind of keeping track of the expected utility in counterfactual scenarios, and the multiplicative term is keeping track of the probability that you like your a priori probability to end up in the branch in which you're ended up. But there's also another way which I personally think more elegant to think about it, where instead of dealing with those things, you're just thinking of expected value as a function of functions, right? So like what do we have? What are probability distributions even for? Therefore, you can take it. Probability distributions are just gadgets for taking expected values. And in classical probability theory, these gadgets are always linear functionals. So every probability distribution gives you a linear functional on your space of functions, like the space of things that you might want to take an expected value of.
And concretely, this functional is like taking a function from your, I don't know, event set to the real numbers, and this functional is taking, okay, on average, what's the value of this function given my distribution over like what the true event might be, and this ends up being linear in what the function from events to real numbers is. Just to clarify that for the listeners.
Yeah, exactly. So in classical probability theory, there's like a classical theory which says that you can just think of probability distributions as linear functionals. Like you can literally just like consider all linear functionals. They're continuous, and like there's some technical mathematical conditions. They should be continuous in some topology, and they should be positive. So like if your function is positive, the expected exchange also should be positive. but then you can just like define probability distributions as functionals. It's just like equally good way to define them. And then the way you go from classical probability theory to Infra-Bayesianism is, instead of considering linear functionals, you consider functionals that are monotonic and concave. So monotonic means that you have a bigger function, it should give you a bigger expected value. And concave is concave. When you're averaging several functions, your value should only become higher. And you can consider just all of those concave monotonic functionals, and those are your infra distributions. So the fact they're concave, you can intuitively think of it as a way of making risk-averse decisions, basically, because that's what corresponds to this Maximin rule, and that's why those things are also used in economics sometimes, because you want to be risk-averse.
Okay. So we have these infra distributions, which are kind of the same thing as these concave monotonic functionals. Yeah, in this case where I'm not sure, I'm just there's an infinite sequence of bits, and I have no idea what the even bits are going to be, but I have some guess about the odd bits. Maybe they're all zeros, maybe they're all ones. I have a variety of hypotheses for what the odd bits might be. What does my infra distribution look like?
Right. So every hypothesis is a particular infra distribution. If your hypothesis is in example with sequences of bits, you would have hypotheses that only say things about the even bits. You would have hypotheses that only say things about the odd bits. You would have hypotheses that say think about all bits. You would have hypotheses that only think that the XOR of every bit with the next bit is something, or whatever. And basically the convex set, if you're thinking in terms of convex sets, then your convex set is just the convex set of all things that have a particular property. For example, if you're thinking of okay, my hypothesis is all even bits are zero, then your convex set is the set of all distributions that assign probability 1 to the even bits being zero. So in this more general thing, you have SA distribution, so on. But that's just a technicality. That just means you need to take your set of distribution and close it by taking the Minkowski sum with some cone in this Banach space. But that's really just a technical thing.
Okay. So is the idea that I have that for each specific hypothesis I might have, I have this I have this convex set of distributions, and I'm going to be doing this Maximin thing within that convex set of distributions. But is the idea that I'm going to be basically just Bayesian over these hypotheses, and how the hypotheses internally behave is determined by this Maximin strange update type thing?
Sort of, yeah. I mean, there are multiple ways you can think about it. One way you can think about it is that your expected utility, your prior expected utility, is take expectation over your prior over hypothesis, and then for each hypothesis, take minimum of expected values inside this convex set. Or you can equivalently just take all of those convex sets and combine them into one convex set. You can literally just take okay, let's assume we choose some point inside each of those sets, and then we average those points with our prior. And the different ways of choosing those points, they give you different ways of they give you different distributions, and so you get a new convex set. So that's just like in ordinary Bayesianism, right? You have a set of hypotheses. Each hypothesis is a probability distribution, and you have a prior over them, or you can just average them all using this prior and get just a single probability distribution. sort of like two ways of looking at the same thing.
All right, cool. Hopefully, this gives listeners something of an overview of Infra-Bayesianism, and there's, I don't know, if they want to learn the maths of it, they can read the post for the mathematical theory. Going forward a little bit, so it seems like this is a theory of you have a single agent that's inside a big scary environment that's really confusing and complicated, and the agent doesn't know everything about this environment. I think in AI, we like to think of this I don't know, some kind of progression from a thing that's reasoning about the world to a thing that's acting about the world to the situation where you have multiple agents in the world that are jointly acting, and their decisions affect each other, like game theory. Um, so I'm wondering, is there infra game theory yet? And if there, or if there isn't total infra game theory, has there been any progress made towards creating it?
Yeah, so that's a good question. In fact, one of the very interesting applications of informationism is exactly to multi-agent scenarios, because multi-agent scenarios are another example where ordinary Bayesianism runs into trouble because of this realizability assumption, right? If we have multiple agents and each of those agents is sort of trying to understand the other agent, trying to predict it or whatever, then we again get this self-referential paradox. Like we can have a situation where agent A is more powerful than agent B, and therefore agent A is able to have B inside its hypothesis space, but we usually cannot have a situation where both of them have each other in their hypothesis space. So there are like sometimes ways you can kind of have some trick to go like there are reflective oracles, which is a work by Miri that sort of tries to solve it and have agents that do have each other inside each other's hypothesis space, but it's very fragile in the sense that it kind of requires your agents to be synchronized about what type of reflective oracle, or like what type of prior they have. They need to be like synced up in advance in order to be able to kind of close this loop, which is a weird assumption. Um, and Infra-Bayesianism might give you a way around that, because Infra-Bayesianism is precisely designed to deal with situations where your environment is not precisely describable. And in fact, it does give you some results. So you can immediately, for example, it's just trivial to see that in zero-sum games, Infra-Bayesianism gives you optimal performance because, well, that's kind of trivial because Infra-Bayesianism is sort of pessimistic, so it imagines itself playing some kind of zero-sum game. But I haven't really written this is like some uh, open problems, some kind of area where I wanted to work, but I haven't really developed it yet. But it seems like, for example, one result that I believe you should be able to prove is that information agents that are playing a game in a non-cooperative setting will converge to only playing realizable strategies, and then you will have a guarantee that your payoff will be at least the maximum payoff inside a space of non-realizable strategies. So that's already a non-trivial guarantee that you cannot easily get with Bayesianism.
Okay. And yeah, I guess related to the open work. So you late last year, these results were put online. I'm wondering how the reception's been and what open problems you have and how much development there's been on those.
Yeah, so by the way, did I say realizable? I meant rationalizable. Okay. Uh, Yeah, so currently we continue to work on developing the theory. We have a ton of open research directions. So, like I said, we want to apply to embedded agency. And we have another post coming up which kind of gives some more details about like decision theoretic aspects of it. And the game theory thing is like another direction. And another direction, by the way, which we haven't discussed, is the relation of this to logic, because there are also some very intriguing ways to make connections between Infra-Bayesianism and logic. And like in some sense, like I have this sort of thesis that says that Infra-Bayesianism is in some sense a synthesis of probability theory and logic, or of, you can think of it as a synthesis of inductive reasoning and deductive reasoning. And yeah, so we've been working on a number of things. Also on like proving concrete regret bounds, because in reinforcement learning theory, what you ultimately want is you want to have like specific quantitative regret bounds that give you like specific convergence rates. And we have derived some for some toy settings, but we want to have regret bounds for some more interesting settings. So yeah, so like there are a lot of direction. There's work we're doing. There are probably multiple papers we're going to write on the topic. So I think the first paper will be some paper that will have like some basics of the formalism and proofs regret bounds under in some like basic assumptions like Infra-Bayesian bandits or Infra-Bayesian MDPs. But yeah, there's definitely a whole avenue of research to be done there.
Okay. Yeah, could you say a bit more about the connection to logic? Because this wasn't quite apparent to me when I was reading the posts.
Yeah, the logic connection is something that I think we haven't really talked much about in the post so far. So the basic idea is kind of simple. Like once you have convex sets, you have a natural operation of intersecting those sets, and there's another natural operation of taking the convex hull of those sets. So in other words, the sets form what's called in mathematics a lattice. Like some sets are inside other sets, and like you have a join and like a mate. Like you have the least upper bound and a like and the maximal lower bound.
Which is basically just you can intersect and you can union.
It's intersect and convex hull because there have to be convex.
Right. Yes.
Yeah. So and that gives you a sort of logic, and actually you can think of ordinary logic as sort of embedded in that thing, because if you have some set, then to every subset of it, you can correspond an infra distribution, which is just like all distributions supported on the subset. And then your operations of intersection and convex hull correspond to just intersection and union. But you also have like things that do not correspond to any subset. And you can think of those things as some kind of a logical disjunction and conjunction, but it's not distributive. So that's like not classical logic. It's some kind of a weird logic. And you can also define existential and universal quantifiers that kind of play well with this thing. And then you can start like, and then what's nice about it is that you can kind of use this sort of logic to construct your information hypothesis. So like if your hypothesis space, for example, consists of what we call infra-POMDPs, which is like the infra-Bayesian equivalent of POMDPs, then you can use the language of this infra-Bayesian logic to specify hypothesis. And that's really interesting because maybe when you do that, you have some useful algorithms for how to optimize, for like how to control those hypotheses and how to learn those hypotheses, which you don't have for just arbitrary MDPs that do not have any structure. And there might also be algorithms for solving problems in this information logic that do not exist for classical logic, because classical logic is often intractable. Like propositional logic is already NP complete, and like first order logic is not computable. But like information logic, well, we haven't really proved anything about that, but like there is this like some hope that it's more computationally tractable in some like under some assumptions.
So when we were talking about Infra-Bayesianism, there were kind of two things that Infra-Bayesianism basically promised us, right? So the first thing was that it was going to deal with the problem of non-realizability in environments, like maybe we just can't imagine the true environment, but we still want to learn some things about it. And the second was that it was going to help us solve these decision problems, like Newcomb's problem, where you can one box or two box, and if somebody predicts, like depending on the prediction of what you'll do, one might be better than the other. And also counterfactual mugging, where somebody flips a coin, and if it lands tails, then depending on what we would have done, if it landed heads, we can be better or worse off. So these are problems where the environment is kind of simulating you and will make your life better or worse depending on your policy in other states. So how does Infra-Bayesianism help us solve these decision problems?
Right. So what happens is that, what does it mean to solve a problem? It means that the agent can build a model of the problem, which will lead it to taking the right actions, the actions that will give it maximal utility. So the question really becomes, like, the usual way those problems are considered is by starting with something like a causal diagram. But here we're kind of taking a step back and saying, okay, suppose that the agent encounters this situation and the agent tries to understand what is happening. It is trying to learn it, to build some model of it. So the easiest way to imagine how this thing can happen is in an iterated setting, when you're playing the same game over and over, whether that's Newcomb's problem or counterfactual mugging. And then you can look, okay, given that my agent is in this iterated setting, what sort of model will it converge to? And what sort of behavior will it converge to? So we're not assuming something like a causal diagram description. Instead, we're letting the agent learn whatever it's going to learn in that situation. And what happens in situations with predictors that predict the agent is there is always this kind of model available, which says, well, there is something in the environment which is doing those things, and I have sort of Knightian uncertainty about what it's going to do. So that means that in my convex set of probability distributions, so I'm reminding that like in Infra-Bayesianism, our hypotheses were convex sets of probability distributions. So in our convex set, we're allowing this predictor, this omega, to make whatever predictions it wants, because there's no way to kind of directly say, well, it's going to predict what I will do. That's like not, the standard, it's like not a legitimate type of hypothesis, like the standard way you build hypothesis in reinforcement learning, right? Like hypothesis in reinforcement learning are you take an action and you see an observation, then you take an action and so on. So this omega can do whatever it wants. But then there arrives some moment in time when its prediction is tested. So omega made some predictions, wrote them down somewhere where we cannot see, and then doing things according to those predictions. And then the prediction is getting tested. And at this point, well, what happens is that if this prediction turns out to be false, then we can imagine that what happens is a transition to some state of infinite utility. So that sounds weird at first, but like why? So why a state of infinite utility? Well, first of all, notice that this is consistent with observations because the agent will never see a situation in which a prediction is falsified, because by assumption the predictor is a good predictor. So this will never actually happen. So it is consistent from the agent's perspective to assume this. But once we assume this, then the optimal policy becomes behave as if those predictions will be true. Why? Because we're always planning for the worst case. And the predictions becoming false can never be the worst case, because if the predictions are false, if they are falsified, then we end up with us in the state of infinite utility. So that can never be the worst case. Therefore, the worst case is always going to be when omega actually predicts correctly. And our policy is going to be the optimal policy given that omega predicts correctly, which is the UDT policy. Now, there is another thing where you can develop it. So initially, I just introduced this idea as a kind of ad hoc thing. But then we noticed that, and that's still in the upcoming post that we're going to publish soon, then we kind of noticed that if you also allow convex sets which are empty, so kind of beliefs that kind of describe the notion of contradiction, like something which is, impossible, and your hypotheses are infra-MDPs, so that's like the infra-Bayesian version of MDPs, then you can, instead of literally transition to a state of infinite utility, you can use a transition where the transition kernel is an empty set. And that's you're just the infra-Bayesian representation of an event that is impossible, like an event which is a contradiction, which this model, this hypothesis, forbids from ever happening. And this kind of explains why you have infinite utility, because our utility is always taking the minimum over this convex set. But if the convex set is empty, then you get the minimum is infinity.
All right. That when you were saying that, I was reflecting on how the infinite utility thing seems like kind of a hack, but the nice thing about that empty transition kernel thing is it sort of more naturally expresses your notion of impossibility, right? Like nothing can happen if you do that.
Yeah, exactly.
So the way this setup kind of works is you're talking about situations where the predictor has some idea of what you're going to do, and then there's some possibility that the prediction is falsified, right? And if you act contrary to what the predictor thinks, then you get infinite utility, and so you don't, the Murphy, the laws of minimization never pick the environment where the predictor guessed wrong. So in the original posts, one thing you kind of talk about as a challenge to this is transparent Newcomb's problem. So in transparent Newcomb's problem, there's box A and box B. Box A definitely contains $1,000. Box B either contains $0 if the predictor thinks you're going to take both boxes, or it contains $1 million if the predictor thinks you're only going to take box B. But the difference to normal Newcomb's problem is that when the agent walks in, the agent can just see what's inside box B. And so the agent already knows which way the predictor chose. And in your post, you sort of describe how this poses a bit of a challenge, right? Because there's no possible way for the predictor to know, if the predictor guesses wrong, and thinks that that if the box were full, then you would take both boxes, and therefore the predictor makes the box be empty, then like the predictor will never know what you will do in the world where both boxes are full. Can you describe how you think about that kind of situation, and if there's anything Infra-Bayesianism can do to succeed there?
Yeah, so this is correct. So what we discovered is that there is a certain condition which we called pseudo-causality, which kind of selects or kind of restricts the types of problems where this this thing can work. And yeah, so the pseudo-causality condition, it basically says that it basically says that whatever happens cannot be affected by your choices in a counterfactual which happens with probability 0. And that's why like it doesn't work in transparent Newcomb when the outcome depends on your action when the box is full. In the version of transparent boxes, when the outcome depends on your action when the box is empty, everything actually does work. And right, because like if what happens is like if the predictor conditions its actions on whether the box is empty, and I decide to one box, then the prediction is not allowed to show me the empty box because then I will one box and will falsify its prediction. So that's something that we call kind of effective pseudo-causality, which means that those counterfactual kind of affect you, but only in one direction. So one way to look at it is you can look at it as a sort of a fairness condition. Like one of the debates in decision theory is like which kind of decision problems should even be considered fair, like in which kind of decision problems we should be expected to succeed. Because obviously, if you don't assume anything, then you can always invent something which is kind of designed to fail your particular agent. Because you can say, okay, omega, if it says an agent of this type, it does something bad, and if it is an agent of a different type, it does something good. So, and this is something which was used to defend CDT, but then like Eliezer Yudkowsky in his paper on timeless decision theory writes that yeah, of course there should be some fairness condition, but that does not justify two-boxing Newcomb's problem, because Newcomb's problem, the outcome only depends on the action you actually take, not on the algorithm you use to arrive at those actions. And this was kind of Yudkowsky's proposal of what the fairness conditions should actually be. So in Infra-Bayesianism, in like the straightforward version of Infra-Bayesianism, the fairness condition that kind of Infra-Bayesianism is able to deal with is the environment is not allowed to punish you for things you do in counterfactuals that happen with probability 0. So the environment can punish you for things you will do in the future or things you will do in a counterfactual, but not for things that you will do in a counterfactual that can never actually, that like has a probability 0. So like it's not even a real counterfactual in some sense. So the way you can like what can you do with this? Like one thing, you can just accept that this is a good enough fairness condition, and maybe it is. I'm not sure. Like it's hard to say definitively. Another thing is you can try to find some way around this, and we found basically two different ways around this. How to make Infra-Bayesianism succeed even in those situations, but both of them are kind of a little hacky. So like one of them is introducing the thing we'd called it survironments. So you kind of do a formalism where you allow infinitesimal probabilities, and then like those counterfactuals that never actually happen, they get assigned an infinitesimal probability, and then it kind of works. But it really complicates the mathematics a lot. Another thing you can do to kind of try to solve it is assume exploration. So just like assume. One thing to notice is that if we take this transparent Newcomb problem, but assume some noise, so assume that there is some probability epsilon such that the box will come out full no matter what, right? So like omega sometimes like just randomizes the outcome. Then immediately this problem becomes effectively pseudo-causal. So because the counterfactual no longer has probability literally zero, everything is fine. So that's just in baseline Infra-Bayesianism. But what you can do to kind of use this is you can just add kind of randomization on purpose. You can make your agent be a little noisy. So that's like basically a sort of exploration, make it sometimes take random actions, which are kind of not the action it intended to do. So like there's the action the agent intended to do, and then like what actually came out. And if you kind of add this noise, then the transparency Newcomb problem effectively becomes equivalent to the noisy transparency Newcomb problem, and you again succeed solving it, modulo like some small penalty for the noise. And there is some argument here that maybe this is a good solution because we know that in learning algorithms, we often need to add noise anyway in order to have exploration. So maybe you can kind of justify it from this angle. But so I don't know. Maybe it's a good solution, but I'm not sure.
When you say that exploration helps, so I see how like if we think of omega, the predictor kind of just randomly changing whether you get like whether box B is full or empty. I see why that kind of exploration is going to help you in this transparent Newcomb scenario. But when the agent is randomly, might randomly one box instead of two box or vice versa, I don't see how that helps because like if like with high probability you're going to pick both boxes when box B is full, and then maybe I guess it's not 100% probability because you're going to explore a bit, but with really high probability you're going to do that. Doesn't omega put you in a room where box B is empty, and then you probably and then it actually like just doesn't care what you do in the worlds where box B is empty, so it never gets falsified?
Okay, so what happens with exploration is that the hypothesis the agent constructs of the environment, it says the following thing. Well, there is some biased coin which is tossed somewhere, and this biased coin is kind of applied to is kind of XORed with the action I intended to take, and like produces the action that I actually end up taking. And then when Omega's predictions are tested, they are tested against the XOR. So Omega doesn't know. When Omega is making its prediction, it has to make the prediction like before it sees the outcome of the coin. So it makes a prediction, and then like the coin is XORed with the action you intended to get, and then like the result is tested against Omega's prediction. So now, if I decide to one box, then Omega has to kind of predict that Omega has to predict that I will one box, because if it predicts that I will two box, then there is some probability that like the coin will the coin will flip my action, and Omega's predictions will be falsified.
But how? Sorry, I guess I'm missing something. But don't you? Okay, part of my struggle is like, wait, don't you like never end up in the world where the box is full? But then it's like, then I remember like, oh, okay, we're actually like taking the minimum over a bunch of things, so that's fine. But if omega thinks that you're going to take both boxes in the world where box B is full, and your plan is to just take one box, but with some probability, it actually takes both boxes. Doesn't that? But because the random thing that's happening is confirming omega's prediction, right? Not disconfirming it.
So what happens is, like, again, your model, like from the agent's perspective, the model of the environment is as follows. There is a biased coin which determines whether the noise is going to happen or not. And then omega makes a prediction of what action the agent will take. Okay, like the intended action is. Omega predicts the intended action. Then the coin is flipped. The result of the coin is XORed with the intended action to give us the actual action. And then the box is either filled or stays empty according to the result of this XOR.
Okay. Now it makes sense how that would work. But you mentioned that you thought that this was not necessarily a satisfactory approach, right?
I mean, it works, but it just seems like a little hacking, a little like not like it doesn't feel super like it doesn't feel like there's like some deep philosophical justification for doing this, and maybe there is, and I just don't see it. But I don't know.
So, and is it right that as long as we're in pseudo-causal environments, the agent does the quote unquote UDT prescriptions, and it kind of gets high expected utility in all of those environments? Is that correct?
Yeah, exactly. So in pseudo-causal situations, like if you take a decision problem, um, if you take like some finite decision problem where there is some omega that can predict the agent's action in any counterfactual it chooses, then and make it like and make an iterated setting out of it, then assuming that like the relevant hypothesis is in our infra prior, the agent will always converge to the UDT payoff. So it will converge to the policy that has the a priori maximum expected utility, given given that the predictor predicts correctly.
So, one thing you mentioned is that when people were coming up with these problems, they were kind of thinking of it in terms of some kind of causal graph, and like we're gonna have things that are reasoning about programs or such. And the Infra-Bayesian approach like really has kind of a different way of thinking about these problems, and it still does well on the ones that have been come up with, except I guess um, for this transparent Newcomb, barring like these changes to the theory. I'm wondering, like, do you think there are other problems out there that are kind of, I don't know, somehow like similar to Newcomb and counterfactual mugging, um, from the perspective where you're thinking about these like causal graphs and agents reasoning about agents, but that Infra-Bayesianism wouldn't be able to do well on?
I don't think so. I think that this approach is kind of very general. I think that, I think that it's true that Miri initially, when started thinking about those problems, they kind of started thinking about them in a particular language, like using like logic or like thinking about programs or something. I think that Infra-Bayesianism is actually the correct language to use in any situation where you have something reflective. Like yeah, like the original motivation for Infra-Bayesianism is when your environment is too complicated to describe exactly, right? So that's kind of the same. This is in some sense the problem of logical uncertainty, right? Like just phrased in a different way. Like logical uncertainty was about, okay, maybe we have uncertainty that comes from the fact that we are bounded agents and not from lack of information. And here, this is exactly what we're talking about. Like, we are bounded agents, so we cannot describe the world precisely. And I think that kind of all of these problems should be kind of addressed using this language, but there are also connections to those approaches in the sense that, like for example, logic. Well, I think I mentioned before that there are connections between logic and Infra-Bayesianism, and there is like some kind of Infra-Bayesian logic which you can define, and and also there is some extension of this Infra-Bayesianism that I call it Turing Infra-Bayesian reinforcement learning, where you have this Infra-Bayesian agent, and it also interacts with some thing which I'm calling the envelope, where it can just run arbitrary programs, and it treats this thing, this kind of computer, as part of its environment, and that actually allows you to use Infra-Bayesianism to kind of learn things about programs, or like you can think of it as like learning things about mathematics in some sense, or like at least the part of mathematics that can be formulated as like writing finite programs, and and it's like a little related to um, problems, like decision problems that involve logical coins, for example, right? Like for example, like the counterfactual mugging, we like the original counterfactual mugging involves an actual physical coin, but then there's also the version called logical counterfactual mugging, where you use a coin which is actually pseudo-random instead of true random. And then like this Turing information reinforcement learning can allow you to deal with that in a rather elegant way. So so I kind of think that all of this class of questions, like for all of this class of questions, information it serves kind of the starting point of like what's the correct language to think about them.
So, I guess one kind of strange question I have. Suppose like somebody listens to this podcast and they feel very inspired. They're like, I'm going to be an information now. That's just how I'm going to live my life. Um, but they spent the past, however many years, perhaps they were a causal decision theorist with classical Bayesianism. Maybe they used Nightingale uncertainty with evidential decision theory. Who knows what they were doing? But they weren't doing proper Infra-Bayesianism. So perhaps, but in this situation, how should they think of themselves? Should they think that this this minimization of all the expected values, should that start like at the day they were born, or the day that they converted to Infra-Bayesianism, or like the day they first heard about Infra-Bayesianism, but like before they converted? Um, and how are there any guarantees about how well you're going to do if you convert to Infra-Bayesianism? Like as a midlife crisis instead of on the day you were born.
This is an interesting question. I haven't really thought about it. Yeah, I guess that my intuitive response would be sort of um, choosing a policy such that your kind of a priori expected utility, like expected utility in the Infra-Bayesian sense, is maximal. So that would be like imagining that you were Infra-Bayesian since you were born, but for some reason doing something different. Because that's also kind of, yeah, that's like how Infra-Bayesian updates work, right? So like the update rule we have in Infra-Bayesianism, it kind of I think we haven't discussed it, but there's something interesting about the update rule, which is as opposed to Bayesianism, the update rule actually depends on your utility function and your policy in the counterfactuals. So, like, the way you should update if a certain event happened depends on like what you would do if this event did not happen, or like what did you do before this event happened. And I think that this kind of fits well with your question, because if you're updating according to this rule, then kind of automatically you're behaving in a way that's sort of optimal from an updateless perspective, like from the perspective where like you should have been information since you were born, but like you're constrained, but you weren't, and this is your constraint. So
Okay. Do you think you're going to get some kind of information optimality guarantee where, like, if I convert to Infra-Bayesianism at age 40, then my utility is going to be kind of the best you could have done, given that you followed your, like, old foolish ways before age 40? Or are you not going to be able to get anything like that?
yeah, I think that you will for like the usual reasons. Like basically you're a learning agent, so you learn things and you eventually converge to something. I mean, it kind of depends on what optimality guarantees you have, right? Like in learning theory, to have optimality guarantees, we usually assume things like that the environment is reversible. Like you cannot do something which kind of shoots yourself in the foot irreversibly. And like that's a different question of how do you deal with that. But like obviously if you kind of did something irreversible before, then you're not going to be able to reverse it. But I think that kind of given that you already did it, you're going to have kind of the same guarantees that you usually have. But by the way, when you started asking this question, it made me think about something different, which is like, how do we apply this to kind of rationality for humans, right? Because like I kind of came up with this in the context of AI, but then you can say, okay, all the things that we say about rationality, like calibrating your beliefs or like making bets or whatever, how do you apply Infra-Bayesianism there? And I'm actually not sure. I think that I just haven't like thought a lot about this topic, but I think that this kind of another interesting topic that somebody should think about.
Yeah, so I guess now that listeners have heard the basics of, or the idea of what Infrabasianism is supposed to be about, and how heard some tantalizing things about a spooky update rule. I encourage them to have a look at the posts. Maybe it'll be a paper someday. If listeners enjoyed this podcast and they're interested in like following you and your work more, what should they do in order to keep up to date?
So the easiest way to follow me is just to follow my user on Alignment Forum or on LessWrong, which is just called Vanessa Kosoy. And of course, if someone wants to discuss something specific with me, then they are always welcome to send me an email. And my email address is also very easy to remember. It's vanessa.kosoy@intelligence.org.
All right. Well, thanks for talking with me today. And to the listeners, I hope you join us again next time. This episode was edited by Finan Adamson.